Good morning, everyone. Thank you all for being here today and for taking the time to attend my presentation, in special for the committee members. Then I'll share my PhD research and on evolutionary-based path planning for kinematic constrained mobile robots, a framework using non-uniform rational B-Spline curves, supervised by Professor Luciano, Frederico, and me. And I must admit I'm feeling a bit nervous, but let's go. Here's an overview of the topics I'll cover in today's presentation. First, I'll introduce the context, motivation, objectives behind this research, and the test outline. Next, I'll present a brief literature review from a systematic literature map. I'll then move into the proposed framework, an offline or online planning, the co-evolutionary approaches for air corridors and multi-agent path planning, and the last component of the framework, the inclusion of photogrammetry-based constraint for inspection. For all, I'll present the problem to solve, the main ideas of the proposed methods, and some results. Next, I'll finish with conclusion, highlighting the contribution, limitations, and suggestions for future research. A kinematic constraining robot is one whose motion is subject to constraints on its position, velocity, acceleration, or high-order derivatives of motion without considering the effects of force. In this thesis, some typical examples of kinematic constraining systems are considered. These include fixed-wing UAVs, as illustrated in this video, which are widely used in multiple application domains. Besides that, ground vehicles such as Archman vehicles and differential drive mobile robots. In many practical systems, kinematic constraints can impose curvature limits and desired orientation requirements at the start or end of the path, make the planning problem more challenging. In addition, ignoring such constraints can result in infeasible or inefficient paths, ultimately compromising the robot's ability to execute the path plan. This issue is illustrated in this example. When planning a path from point A to point B, considering minimal length and safety, traditional planning, such as sampling-based methods, can easily provide a straight line path that appears short and obstacle-free. However, for kinematic constrained robots, like a differential drive robot with a fixed initial orientation, the obtained path in black becomes infeasible and even unsafe when the robots try to follow it. That is, the robot may still end up collision with an obstacle in the environment, as shown in this simulation, as well in the practical situation. To mitigate that, it's common to require a reactive strategy during the motion. This thesis addresses the following fundamental question: how can a planner provide a deliberative feasible path for a robot or a system of multiple robots, considering the robot's inherent kinematic constraints? The challenge of generating deliberative feasible paths for robots in known environments has been extensively studied with predominant strategies including graph search methods, sampling-based algorithms, meta-heuristic optimization. However, several research gaps remain, and our approach aims to address this challenge. First, a common practice is to use a discretized path representation, a sequence of waypoints, and then apply the post-processing smoothing techniques. That is, the plane then smooth paradigm. However, this two-stage approach critically decouples the path planning from the constraint satisfaction. They often do not guarantee that the resulting smoothed path will remain collision-free or respect the kinematic limits of the robot. Second, many existing strategies overlook the explicit consideration of the robot orientation during the path planning. Third, Although certain plan algorithms and methods claim to address kinematic constraints, they lack validation in complex scenarios. For example, scenarios where the environment dimensions are much larger than the curvature constraint do not adequately explore the planner's ability to deal with this constraint. Another gap, not often addressed in previous study, is the challenge of navigating through narrow space considering the kinematic constraint. In addition, planning the motion of kinematic constraint robots in dynamic environments remains a challenging problem. Local plan alone may cause robots to go in local minima or produce unfeasible solution. Our hypothesis is that a path planning framework based on evolutionary approach combined with the flexible and generic representation of Nernst curves can produce feasible, continuous, and high-order differentiable paths that inherently respect the kinematic constraint of mobile robots operating in complex environments, all within a one-shot optimization process. Here, the framework is built on a solution that supports both offline and online planning strategies, accommodates single or multiple robots, and it's applicable to aerial and ground platforms. An evolutionary approach is a meta-heuristic algorithm inspired by the natural evolution. And NURBS is the non-uniform rational B-Spline curve among the set of possible curve representation. We chose NURBS curves because they can offer a flexible, generic, and a unified framework for representing paths. And we address these kinematic constants, bounded curvature, desired initial and final orientation, bounded climbing angle for the 3D scenarios. Our research focuses on developing and validating a path planning framework for autonomous robots subject to kinematic constraints based on parametric curve representation and an evolutionary-based approach. And the specific objective of this study are to explore Nernst curve as a path representation, to develop an offline-online planner, to evaluate the extension of the approach to multiple agents, and to demonstrate application in 3D and 2D scenarios. Here we can see the thesis outline with the respectively publications. The initial ideas for this thesis originate from these two works published in Latin American Conference, one that combined S-Spline-based planning for soccer robots, and another that integrate vector fields with model predictive control techniques. The main work was published in the journal Knowledge-Based System, presenting a novel path planning based on differential evolution and NURBS path representation, taking into account the kinematic constant. After the qualification, 8 studies were developed, 6 already publishing and 2 currently under submission. 2 of them are systematic literature mappings, while others extend the method to online planning and to coevolutionary approach for corridors and multi-agent planning. Additionally, 2 applications were conducted, one for a mini autonomous bicycle, not including this thesis because it was only a direct application of the base method, and another for integrate photogrammetry into UAV inspection. Moving on to the literature review, I've conducted a systematic literature mapping to provide a general overview of the path planning and collision avoidance approaches developed for fixed-wing UAVs in the last decade. To do this, the papers were collected through a well-defined process consisting of these 6 steps. From these steps, we select 345 papers to try to answer some research questions. One of these findings is the main publication source related to path planning for fixed-wing UAVs, and I highlight the ECUAS conference, where most of the papers are published, and ICRA, and some result of this test was also published in this conference. We can see the spatial distribution of the select papers in a 2D landscape map in 15 domains, where the distance between the select papers is related to the domain similarity. Considering the select papers divided into these domains, clearly all domains except domain 4 have been covered more in the last 5 years, the red box in this graph, which indicate the importance of developing techniques for kinematically constrained UAVs. For example, domain 9 has the highest number of papers in the last 5 years, indicate also that many of the select papers treat the path planning problem directly as an optimization problem, as in this thesis. Among them, more than 80% of the papers in this domain were published within the last 5 years, considering solutions involving population and swarming approaches. Considering our problem, different solution strategies to allow kinematically constrained robots to navigate safely through an environment can be compared with our proposal of the offline path planning, the base of this thesis. Artificial potential field-based methods are real-time planners, but usually when considering curvature constraints, they only handle with simple obstacle environments. Geometric-based approach often use dubbings-based paths and do not consider obstacles, resulting in paths with discontinuous curvature at the transition points. In turn, graph sampling-based approach usually represent path as a set of points and very often use a smoother to obtain a continuous curve. Similar to our proposal, nature-inspired approaches could use PSO-DE-based solvers with paths defined by different curves such as splines or B-splines. However, orientation constraints are not considered in this approach do not typically address complex scenarios such as narrow passage or closed loop missions. Thus, my PhD research will go in this direction, aim to contribute a solution to the path planning problem that addresses multiple constraints, orientation, climbing angle, curvature, and obstacles, while considering complex environments. In addition, unlike others' approach, we do not need a smoothing step to obtain the final path. Moving on to our framework, I divided it into these 5 components. Let's start with the offline planning, which was published in the journal Knowledge-Based Systems. Here, we consider a sequence of waypoints, that is a set of configuration, not only the position, but position and orientation in the 3D space. In this way, our problem is to find a feasible path that smoothly make the robot reach all these configurations. And for a feasible path, we can define as a curve that reaches the given waypoints according to the specified order and satisfies the robot constraint: maximum curvature, maximum minimum climb angle, and initial and goal orientation, while avoid obstacle in the environment. In this case, we consider obstacle to be no-fly zone, as illustrated by this green region. This could be an unknown area, an area subject to radar detection, or an area of strong electromagnetic interference. Here is an overview of our planning. A sequence of configuration defines the mission sections, and each section can be solved in parallel by our optimization algorithm, the Elias cop, resulting in a set of section paths. Each path is represented by a nerve curve, as I'll show next. From this section path, to obtain a single parametric path and to send to the control module, we use nerves properties to guarantee a fully smooth path through a geometric joint method. Then, the paths are defined using a non-uniform rational B-spline, the nerve curve, shown in this equation, where S is the parametric variable, Pi are the control points, and you use NP control points. For example, in this curve, we have 9 control points, P0 to P8. In addition, B represents the B-spline base function obtained recursively from this equation. In the picture, you can see the B-spline base of a 3-degree Nubs curve. To obtain this, we define a knot vector composed of m elements between 0 and 1. And finally, unlike B-spline curves, Nubs has a 8 for each control point. As the animation shows, by change at 8, we can locally modify the curve. This gives a great deal of flexibility to the nerve curve, even without change the control points. To induce the initial and the desired yaw angles and the desired climbing angles, we can define the following 4 control points, 2 at the start and 2 at the end. As shown in this animation, we can induce the desired angles, change these control points. Our problem can be written as the following unconstrained minimization problem, defined as a weighted sum of functions ft, where ft is a sum of objective functions and the sum of the constant penalties. The optimal solution in this case, key star, is the optimal free path parameters based on the nerves representation, the control points, 8, and the lambda values. Here we can see a list of these functions. Our objectives are to minimize the total path length, reduce the vertical movement, and ensure convergence to the desired orientation. We also include penalties for violating the maximum or minimum climbing angle, exceeding the maximum curvature, and for colliding with obstacle, and leaving the allowed flight space. To solve this optimization problem, we employ a differential evolution-based algorithm. The DE algorithm is a population-based algorithm that simulates the process of natural evolution. It works as shown in this flowchart, iteratively exploring the solution space through mutation, crossover, and selection operations. SHAD extends the original differential evolution algorithm by introducing self-adaptation mechanisms to dynamically adjust control parameters during the evolutionary process. LSHAD extends the previous algorithm by introducing a linear reduction in the population during the evolutionary process, by gradually reducing the population size. Finally, our proposed algorithm, the LSHAD copy, introduces a mutator and a selection mechanism based on feasible solution to effectively address our constrained optimization problem. The proposed operator mutator is named the best feasible hand to take into account the best individual in the population, but first available in the feasibility criteria. And similar, the selection also prioritizes the feasible solution. Now let's explore of our finds. We evaluate the ability of the algorithm to generate feasible paths in different scenarios, obstacle-free, a single no-fly zone, changes in the environment with many no-fly zones, and topography, complex environment, and narrow passages. We also compare our proposed optimization algorithm with 6 nature-inspired algorithms. Considering the obstacle-free environment, for that, we use the benchmark described in VANA 2020 for 10 instances. Our method achieved a similar result to the related works, provide a curve similar to a Dubs curve, as shown in these figures for one instance. However, unlike related works, our proposal provides a continuous curvature very smooth. For example, in VANA approaches, we notice that at the transition point between a straight line and a circular arc, the curvature is not continuous. Next, we'll skip ahead to the complex scenario involving many obstacles, narrow passageways, and a closed-loop mission. In this case, each section of the path was obtained by parallel processing, and then the joint curve algorithm was applied to generate a complete parameterized NURBS path. Here is the result, where the curvature and the climbing angle for the complete path are satisfied. In this next scenario, we test the flexibility of the NURBS representation, considering a small tunnel. This animation shows the evolution of the path to converge into a feasible solution. In addition, we compare the NURBS representation with the B-Spline representation. We can see that in this case, the B-Spline approach does not satisfy the curvature constraint, indicating the flexibility promoted by the NURBS representation. These 6 nature-inspired algorithms have been selected to be compared with our proposed solver. This is the result of the comparison. Many of these algorithms did not converge to feasible solution. In any case, they found local optimal solution, short paths, but did not satisfy our constraint. For example, in this scenario, these algorithms highlighted here provide a collision path with the no-fly zones. Considering the algorithm that find feasible solution, our algorithm found found more feasible solution, 98.5% of the case. And beside that, statistically, our proposed algorithm has a significantly better performance compared to the CDE planner. Moving on to our online planning, published last year, our early result, in this year the complete version at the ICRA. In this study, we consider a scenario where an UAV has desired cruise speed within a limited range. For example, when we work with fixed wings, they have a minimum speed different from 0. That is, they cannot hover or remain stationary in the air. Besides that, they have a limited curvature. You assume, in this case, also a bounded speed disturbance in the low-level control. Our proposed approach contributes to provide an online and deliberative path planning to address kinematic constraints such as maximum curvature and the orientation of the robot, continuous curvature profile, collision avoidance for static no-fly zones, and dynamics obstacle, for example, non-cooperative and non-adversarial UAVs in the environment. The key ideas of our proposed approach are a parametric path representation, the optimization problem with the velocity obstacle integration, and a control-aware parameter. We are also working with paths represented by NURBS as before. However, since the robot is assumed to move along the curve at a constant speed, the NURBS trajectory can be mathematically expressed as follows, converting the parametric s to time. To obtain the parameter of the NURBS curve, we need to solve an optimization problem each replaning time. Our optimization problem is minimizing the length of the curve, also the change in the cruise speed and keeping close to the previous control points of the curve. Take into account the speed range, the maximum curvature, and the velocity obstacle space for all obstacles. Note, unlike before, here we search for a variation of the control points, the aids of an initial nerve path. To check the temporal collision with dynamic obstacles, you use the idea from the velocity obstacle space described in this equation. This space is based on the relative position and velocity of the detected obstacles. This ensures that if the robot follows the optimized path, there will be no collision with detected obstacle within a time horizon represented by tau. Besides that, we add a control R parameter in the plane based on this robust vector field as proposed in Resende 2022. This ensures robust curve following under disturbance in speed, considering the invariant set I. This invariant set is like a tube around the path. Then we inflate the obstacles with this parameter in our avoidance constant. The replane strategy can be visualized here, starting from an initial path, for example, a straight line. At each iteration, we search for the best variation parameters of the previous path, performing a continuous optimization as the environment changes. First, we update the local information by finding the closest point on the path and cutting the curve at that point. Next, we solve the optimization problem, now considering the velocity obstacle, while the solver searches for the best solution. The previous path is tracked using the robust vector field. Once the solver provides a feasible solution, the path is updated and the iteration begins again. Here are some of our results. You can observe the robust vector field responsible for tracking the curve, as well as the updates performed on the path during the replaning process. The plots also show the curvature profile throughout the motion, showing that the robot can reach the desired final pose while respecting its kinematic constraints. Next, we can see a comparison in cluttered scenario, 50 obstacle. On left, our motion plane, and on the right, the non-reactive velocity obstacle approach. Our method successfully satisfies all constraints, including curvature and speed limits. However, the reactive VO approach failed, causing the robot to stop or even leading to an unfeasible scenario, causing the collision. Now, considering a real robot experiment with a crazy fly. Firstly, we estimate the disturbance in the low-level speed controller, and here we show the result with 5 virtual obstacles. The blue region here represents the limited sense range from which only local information is used during the replane. And the gray tube corresponds to the invariant set, which defines the region within which the robot is guaranteed to remain due to the robustness of the controller. The third component of our framework is our air corridor plane, which we present at equals. Now, considering another problem related to the altitude airspace management, to address this challenge, new formulation of controlled airspace must be developed, such as the introduction of design air corridors or UAV traffic lanes. These corridors are similar to highways, but in the sky, like a tube allowing UAVs to travel safely, efficient, and in compliance with regulations. For that, we consider some areas where the UAVs cannot circulate, the no-fly zones, and safe zones designed to comply with regulations in different types of UAVs. To specify that, we set the height and the width of this safe zone. As input of our algorithm, we consider a set of non-vertiports, that is, land takeoff regions, represented as cylinders. We define a feasible air corridor that connects two vertiports, satisfy the following condition. It avoids no-fly zone, it avoids intersecting with other air corridors in the environment, it remains within a specified altitude safe zone, and it adheres to a specific maximum curvature constraint. Then our problem is to find a feasible air corridor considering these requirements. Our proposed method is dividing air corridor representation, the definition of the optimization problem, and cooperative coevolutionary approach. We propose that the central path begins and ends at a tangent point on the boundary of a vertiport. This approach allows for smoother operation and improved coordination for UAVs that cannot hover or remain stationary, by providing a continuous path to guide the UAV into a circular holding pattern before landing or takeoff. Each central path is also represented by a NURBS curve. Our optimization problem is defined as the minimization of the sum of all path lengths while satisfying several constraints, remaining within a designed safe zone, avoiding collision with obstacles and with other paths, and respecting a maximum allowed curvature for the air corridor. The optimal solution in this case corresponds to the set of paths connecting each pair of vertiports. This is a hard problem, so we propose a cooperative coevolutionary approach. Here is the general idea behind it. The original problem is divided into n sub-problems, each formulated as an optimization task that minimizes its own path length while satisfying its corresponding constraint. These sub-problems evolve for a field generation use the Elias algorithm, which incorporates shared information, in this case, the best path obtained from the other sub-problem. Using the current solution of all sub-problems, we then compose a full candidate solution. It's evaluated as a whole. If this new global solution is better, it is kept for the next cycle. Otherwise, the previous solution is preserved. This process repeats. Solve each sub-problem, exchange information, assemble the complete solution, evaluate it, and continue until the stop criterion is reached. Let me show some results. This animation presents the 15 air corridor paths generated by our planning, illustrating how they evolve to minimize total path length while avoiding the central no-fly zone and remain within the safe altitude regions. This scenario contains 20 vertiport pairs and 10 no-fly zones, both handling generated. Note that each vertiport is also an obstacle in the air corridor, so there are 50 obstacles in this environment, very cluttered, and the algorithm can find the solution in few generations. After that, it continues refining and reducing the total path length. Let's move into our multi-agent planning. the fourth component of our framework, which is currently being processed for journal submission. Now, for this problem, we consider the multi-agent path planning problem in a continuous 2D workspace for any non-autonomic robots, differential-derived robots. Each robot must navigate from a given start pose to a goal pose while satisfying the following feasibility requirements. Temporal collision avoidance. The robots must avoid collision with each other, considering the time. Obstacle avoidance. The robots must avoid collision with static obstacles in the environment. And kinematic constant. This constant is expressed by the desired orientation and as a bound of the maximum curvature of the robot. Each robot is a differential-derived platform with linear and angular speed inputs. This implies that the maximum admissible curvature is given by this equation. We also assume that each robot has a predefined speed, which must lie within a constrained range. In addition, we consider that a low-level controller enforces a closed-loop behavior that approximates a single integrator subject to a bounding speed disturbance. As before, is important because once the optimized path is obtained, we apply this robust vector field, which yields an invariant set. This invariant set provides a safety margin for the plane used to guarantee collision avoidance even in the presence of the disturbance. The path is represented by nubs. Unlike before, now we use a uniform notch vector, which requires assign k plus 1 repeated control points at both the start and the end position. This configuration can benefit the speed control because all derivatives up toward the k at the start and end points become 0. Additionally, 2 extra control points are added, aligned collinearly with the start and end points as before to ensure the desired orientation. And for the optimization, we have NP control points given by this equation. Our problem is to find feasible paths and corresponding linear speed that minimize the total travel time of our robots and keeping close to the predefined speed. These constants are related to obstacle, curvature, speed limits, and the bounded search space. By considering a constant linear speed and apply the arc length transformation here, we obtain the corresponding nubs trajectory. The optimal solution vector then includes the solution for all agents, that is the path and speeds. This is also a hard problem, so we propose solving it using our cooperative coevolutionary approach previously applied in the corridor context. The complete problem is divided into any subproblem, which involves for field generated using Elias copy algorithm. The evolution incorporates shared information. In this case, the best path obtained, the best path and the best speed obtained at each epoch. Here we present some results obtained in the robotarium environment. Each robot must reach the position directly opposite its initial location. Each path is enclosed by a tubular region that represents the safety margin, account for possible error in the low-level speed control, and we can observe the evolution of the paths over 20 epochs. After only a few epochs, the paths already become feasible, and here we show the real experiment in the robotarium environment. You can see the robots avoided the collision. In this second scenario, 2 robots must reach the opposite side through a narrow corridor where only one robot can pass at a time. A small escape area is available, allowing one robot to temporarily move aside and let the other pass. This setup evaluates the plane's ability to generate an optimal coordination strategy that minimizes the overall mission time. In this third scenario, 4 robots must reach their respective goals in an environment containing 8 obstacles, represented as polygons. In one of this region, the obstacles form a narrow passage that allows only one robot to pass at a time, making the optimization problem significantly more challenging. Moving on to the last component of our framework, the photogrammetry-based path planning for inspection. Now we consider different contexts. A commercial UAV inspecting large 3D structure, as illustrated here. The problem we aim to solve is to generate a motion plan, an optimal path that ensures photogrammetry and kinematic constraints, and guarantees safety by avoiding collision with obstacles in the environment, even under bounding disturbance in the low-level speed control. To achieve this, we use the robust vector field used before to guide the UAV along the path. Additionally, we introduce the idea of zone of importance, representing regions where relevant information is more likely to be found, for example, cracks and hazards. In these zones, it is desirable to increase the image resolution captured by the UAV during the mission. Here we can see an overview of the proposed method composed of online and offline steps. In the online step, the same vector field used early is applied to follow the optimal path. To track the curve, we use GPS to obtain the UAV's current position. In the offline step, you consider the maximum allowed curvature determined by the drone's maximum lateral acceleration and speed. The zone of import are known in advance, as well as the environment, which is obtained from initial high-altitude flight that provides a pointed cloud, as shown in this figure. The initial path together with the photogrammetry constraint serve also as the input to the planner. To obtain the complete path, you divide the problem of any sections, as illustrated in this figure. The start and end points of each section must be free of obstacles, and our planning approach solves each section independently, computing the variation in the control points and aids relative to the initial path. The first environment is a tailing dam, for which a point cloud of the area is provided beforehand, and running the planning for the 47th section, we obtain these results, successfully covering all the areas of interest, avoiding the obstacles. Focus on one of the sections, we compare our planning with a recent work published at ICUAS, which use A-star planning combined with B-Spline interpolation. Both paths are smooth, however, in avoiding the obstacle, the solution produced by the A-star-based method does not satisfy the photogrammetry constraint specified by the indigo region in this figure. Now, in a similar but smaller environment, we test our complete solution at Waterdam in the United States, West Virginia. An initial back and forth path is provided, and our planning generates an optimal path that accounts for 2 zones of importance. The reference distance is set to 20 meters from the area of the interest. The overlap can change from 80% to 60%. The drone performed descent motion near the zones of importance to increase image resolution, as can be observed now. Without the zone of importance, the drone keeps the reference distance. At the end of the mission, all collect images are used to generate an orthomosaic map. Here we can see the improved detection of the three objects located within the zone of importance. Concluding, I present our complete framework. I can highlight some contribution. First, a formulation of the nerve-based path planning as a kinematic constraint optimization problem for static and dynamic scenarios. Propose of a cooperative evolutionary strategy for air corridor generation and multi-agent path planning problem. Integration of photogrammetry requirements into the constrained path planning problem, considering zone of importance, where the resolution of the imaging can be increased. And from the experimental contribution, we can highlight the validation simulation against a diverse set of evolutionary-based algorithms and path planning methods. Real-world experiment with UAVs, including indoor quadrotors, crazy flies, and a commercial drone, as well as with differential drive robots. Together, these contributions demonstrate a unified approach for generating feasible paths across different contexts using NURBS representation and the evolutionary-based optimization method. Although the proposed framework achieves our objectives, I can indicate some limitations. First, the naive implementation that affect the efficiency of the online method. The LSHAD solve was evaluated only for the specific problem addressed in this study. Third, the online planning assumes full knowledge of the robot's position and velocity, which limits its applicability in environment with non-dynamic obstacles. And finally, we didn't explore the scalability of the solution. Based on these limitations discussed previously, several research directions can be pursued to further advance this work. From implementation perspective, parallelization strategies such as GPU, FPGA acceleration could be explored. Regarding the optimization, the framework can be extended to handle with multi-objective formulations, evaluation of the proposed method for general benchmarks, evaluate the proposed method for that, adaptation for onboard sensors such as LiDARs, incorporate of the direction and speed of the flow, and evaluation of a vector field-based control strategy that explicitly accounts for curvature constraint. Here's some reference, and thank you. I briefly, first of all, I want to thank God for everything in my life and for surrounding me with so many people who made it possible to reach this dream. Here, a big thanks to my family. Here's my wife, Michelle. We are always together, even attend a robotic conference with me. My dad and my mom. Today is my dad's birthday, so this is my gift to him. All sacrifice they made for me were worth it. My sister, my mother-in-law and sister-in-law, my large family, aunts, uncles, cousins, godchildren, all friends and brothers from the community missionary of Vilareja. Thanks to my colleagues and friends from IFMG, UFMG, Corulab, Faro, Minds, Cefet, FOP. And I also grateful to my students. My vocation as a teacher has made this PhD special. And I would like to thank my supervisor, Luciano, Frederico, and Miri. Thank you for your patient insights and feedbacks. I'm very grateful to you all. I feel that I was really well supported. And I truly stand on the shoulders of giants. It was a great honor for me to meet Rosena Bashi, my academic great-grandmother. In this way, I also thank this academic line, Professor Mario Campos, Guilherme here in the committee, to whom I extend my acknowledgement for guiding me during my undergraduate and master studies, and for also open his lab in West Virginia to me. It was a very nice experience. And thank you again, Luciano. You made many hours available for me, and we had the opportunity to attend conferences together in the Netherlands, the United States, and here in Brazil. Finally, I also need to thank the financial support from FAPEMIG, INCT, CNPq, CAPES, VFMG, and my institution, IFMG. Thank you all.